I'm back. Still a game developer, by the way. And you can still go to my portfolio website and still go download my games and check out my stuff. Okay, so in the last video in this series, we covered how to move a character around, and I showed you some of the systems I've used and put in place. So it only makes sense that in this one, we cover how to actually read inputs and what to do with them and where to take them. Alright, so given we're using finite state machines, go watch the other video if you don't know what that means. Input should be read one time and then used to move into another state, instead of just being read constantly in an update function. Why? Well, this leans heavily into another pattern I use quite a lot while making this game, the signals and listeners pattern. Okay, the gist. So instead of pulling for something every frame in an update function, you instead create a class or script that is all about pulling and listening for this one thing. In this case, input. Though, luckily, Godot is already pulling for inputs every frame. So all we have to do is use the input event function that's built into the game engine to grab whatever it pulls. Once we grab the input event from Godot's pulling, then we can scrub through the data and make sure it's what we care about. If it is, we pack it up into a signal of our own and then send out that signal to whoever cares. And this is all housed in the player controller that we talked about last video, so anything that does care about player inputs has to go through the character controller brain. Luckily, our finite state machines can do just that. And because of the way we've packed up the input event and sent it out as completely separate signals based on the input we care about, all the states have to do is say, I want to listen to this input because it's the only one I care about. Say neutral, for example. You remember neutral from the last one? It cares about a lot of different inputs, so it subscribes or listens to different ones. If the move left or right input was pressed, well, move into walking. If up was pressed in any capacity, move into jumping state. Down, crouching. But then there's other states that don't really care about inputs at all, really. Say in the action finite state machine, the hurt state. As I said in my last video, if you're in the hurt state and you're getting comboed, you can't really move your character at all in most games. But we do still have to do it to listen for attack buffering. And speaking of, input and attacking are more intertwined than any other state. But in order to dive into the attack state, we also have to talk about moves or attacks and their properties. The goal of these videos is to help people think like designers and really scope out everything that's required to make stuff like this. So I had to sit back and figure out what are attacks? What are moves really about? What are the data points that make them function the way they're supposed to? So in order to not reinvent the wheel and continuously spin my own wheels, I decided to look at other games. A teensy bit of studying on Street Fighter 6, Street Fighter 3, Tekken 7, Tekken 8. I looked at all of the available in-game information as well as information found online made by fans. I never looked at any code though, so I had to use all this information and determine how I would design my own systems, my own architecture. So with all this in mind, let's run through an attack state lifecycle. Let's look at how the input listener is connected to the attack state, and how the attack state uses moves properties to determine whether they should move forward or not, and how that ties back into input listening again. For now, let's ignore setting up character data and move information ahead of time. Those are just used to parse things quicker. When we enter the attack state, we're immediately sent to do our main job, find an attack. Step 1 is determine whether or not a move even exists based on the button that we press to get us into this state. If we pressed, let's say, the light kick button and there is no light kick move at all, then we don't need to search. We know there's nothing. If there is any move on that button at all, then we move into the looping process. Here, based on the button that was pressed, we loop through every move that has that button associated with activating it. Now that we're in this loop, it's time to determine if this move is even doable given our current circumstances. Okay, from here on out, I want to use this move as an example. Now that we have a move that we're using as an example, let's go back to that loop and determine whether or not this move will come out. First thing is we check its pre-requirements. Stuff like the player character's current position or the player character's current state, both movement and action. If these things don't align, then the move won't come out. If all of that is passed and the move continues through the loop, then we get back to inputs. The first thing we have to do related to inputs is determine whether or not the attack button that was pressed aligns with the current move we're looping through. In this move's case, we're checking to see if light kick was pressed. This is based on the move's final button in its button combination. In order to describe the next few things that are related to input, I need to talk about input listener just a bit more. The input listener tracks and stores a lot of extra information that is necessary for games that have specific input combinations like this. For example, it tracks what's currently being pressed this frame, and until you release that button, that will stay stored. It also stores a history of motion inputs. After a specific amount of time, the earliest pressed motion is deleted. This is done to ensure a few things, but it's mostly to ensure that when the attack state wants to look at the player's motion history, that only the most relevant recent motion is taken into account. While that is its most important job and its most relevant job to what we're talking about here, it also does a few other things. It has the timings on backdashing and forward dashing. Say you press back twice, trying to backdash, it determines whether or not it was quick enough and then emits a backdash signal. It does the same process with grabbing. Let's say you wanted to try to grab the opponent with light kick and light punch. It determines whether or not you pressed it quick enough for that to be a grab signal and then emits that signal. Finally, it has tables that allow you to quickly determine if an attack was a punch, a kick, or whatever. All of these things are utilized by the attack state to determine whether the attack gets through. Okay, back to the loop. Next, and this is a big one. If the move is a motion, in this case that's true, it is, we're doing a quarter circle backwards, we have to parse the motion input. This does a lot of things. It determines whether the motion was done in the correct order. Determines whether the motion was done in the correct time frame. Determines whether the motion has too many gaps in it or too many errors in it. I'm going to refrain as much as I can from going into the code of how I made this work, although I would love to explain more. So if you're at all interested in hearing me dive into these things, get into the nitty-gritty technical details of how I made them work and the code related to it, let me know. I'll talk about this stuff all day if given the chance. Anyways, if the motion is deemed successful, even given some errors and gaps, then we continue. The final step here before we can say the move's doable is going through a few yes or no questions based on the move's properties. This move that we're looping through doesn't really care about these questions, so we're going to skip over them. So finally, this means that the move is doable. So we send it to the main attack state. While the player attack state was responsible for hooking into input listeners and determining whether or not the attack should be done or not, the main attack state takes the move that makes it through and affects the actual gameplay of the game and allows it to interact with the systems that make the gameplay function. Okay, now look at this move's animation. You should see that he cartoonishly flies across the screen. Well, I could just use the animation track in Godot to make the character move from this point to this point. Say the player does this move, and the character runs into a wall while trying to fly across the screen. By not doing this in code, I'm relinquishing my ability as a programmer to do something fun based on that idea. This isn't in the game, but maybe I wanted to allow them to jump off of the wall during this move if they touched it. So in order to allow for this possibility in the first place, and to ensure that moves play nicely with other systems in the game, the attack state handles this during its update function. Every frame, it's looking for a velocity property within the move's dataset. If it finds one related to this specific frame, then it goes in and changes the character's movement velocity based on whatever set in the move's properties. The attack state does many other things too that affect gameplay in the same way, like updating hitboxes and hurtboxes depending on the frame, but I'll get into hitboxes and hurtboxes in my next video. For now, just know that all of this is done within this main attack state. Hey, like and subscribe if you think I did a good job and you think I'm cool and funny. I think those things, so I'm personally going to subscribe. Also, make sure to check out my website and play my games and stuff. Thanks!